Okay, good afternoon. So today, all right, good afternoon. Let's settle down. Today we're gonna begin with BJT, bipolar junction transistor, by far the most important solid state device. This was also the first solid state electronic device that was presented. Okay, so the original prototype was presented in late 1940s, 1950, 1940s, and there were three scientists: Walter Brattain, William Shockley, and what's the names is escaping me. But they were working at Bell Labs at the time, and they won the Nobel Prize for their efforts. Okay, so we'll do a little bit of background theory, but for the most part, I want to go quickly into systems perspective, right? That's what this class is about, and that's what you're doing for Lab 3 next week. Okay, so that's why I'm temporarily skipping over the diode circuits and covering BJTs today. So, all right. So before we begin, let's look at that. Why is it one missed connection? Okay, hold on. Okay, there we go. All right. So multi-terminal devices. So far, we looked at a diode. A diode is a two-terminal device, one anode, one cathode, two semiconductor materials, P-type and N-type, and you have one junction, right? That's the most basic of all semiconductor devices. Now, we're going to take a look at multi-terminal devices and how they behave. So how we analyze circuits using multi-terminal devices. There are 3-terminal devices, 4-terminal devices, even 5. But for this class, pretty much we are restricting our studies to 3-terminal and maybe a little bit of introduction to 4-terminal devices. Okay, so it doesn't matter how many terminals the device has. All the laws of electric analysis still apply. If you're talking about general environmental conditions at room temperature, room pressure, atmospheric pressure, then the normal laws, KVL, KCL, Ohm's law still apply. So if we have a device, whether it's linear or nonlinear, KCL still applies. So here we are looking at a 3-terminal device, and the 3-terminal device, we're just marking currents as all going in. Okay. Obviously, with KCL, which is based on law of conservation of energy, that's not really true. These are simply reference directions, right? If a current is going in, stands to reason, then something else is coming out, either one terminal or both the other terminals. Okay, so keep that in mind, because a transistor, this will be one of the fundamental operating principles of the transistor would be current is entering through one terminal and exiting out of the other. And well, current's actually entering from 2 terminals, exiting out of 1 terminal. Okay. And then node voltage analysis that you might have studied in 115 perhaps. We can apply node voltage analysis or nodal analysis at the outer terminals also. In the PN junction diode, we saw that we have an anode and a cathode. The difference in potential between the anode and cathode is dependent on the geometry, the material, and the doping profile, right? So we can describe, fundamentally, we can describe that the voltage is at either end of a diode as V1 and V2, and we can still say, for analysis purposes or explanation purposes, that currents are entering into the terminals, okay, into the terminals. Now, multi-terminal devices, as I said, we want to look at BJT. That's our primary focus. So BJT stands for bipolar junction transistor. In general, not in general, this is the symbol for a bipolar junction transistor. Okay. It's 2 angle lines, and you have 3 terminals. And we'll talk a bit more about the arrow and the junctions. But right now, just let's focus on the terminals because we're going to analyze a system based on these terminals, right? So this is known as the collector. The terminal with the arrow is labeled as the emitter. And then the third terminal is the base. C, B, and E. Okay, C, B, and E. Could you prop that open if you don't know? Thanks. So C, B, and E. Let's think back to the time I mentioned the vacuum tube. You remember I said the first vacuum tube had 2 electrodes, hence the name was diode, 2 electrodes. And then later on, they inserted a third electrode along the cylinder shape to control the flow of current between the anode and cathode. Does anyone recall? Remember that? Right? So the base functions similarly. Okay. In a very generic way, or a crude analogy, we can say that this bipolar junction transistor, this transistor BJT, is a solid state version of a vacuum tube triode. Okay. The current is actually flowing in this direction from collector to emitter. And then the base controls the flow. Yes. This question being asked is, what is the difference between this and a switch? I assume that you were talking about a transistor-based switch. Switches with a transistor. Was it this symbol? Oh, was it something like this? Oh, that's just a mechanical switch. Something that we see on the walls. So it's just to show in the arrow. So basically there's a wire pathway, and then the switch is basically this symbol right here. That's it. That just represents the mechanical switch that we see. That's completely different. It's not. I can address that after outside of class time, but that has nothing to do with the solid state device for now. Okay. All right. So what was I saying? Oh yeah. So we have current flow going from the collector to emitter, and then the base is the third terminal that actually controls the flow of current. Yeah, it controls the flow of current, which is not possible in a diode, not directly at least. Right? In a diode, we just have, you apply voltage, diode turns on, forward bias, current starts flowing. If we wish to change the flow of current, then we must change the supply voltage or the supply current. But we cannot apply another signal on top and control the flow of current directly. Okay. So in a transistor, we can do so because we have a third terminal. All right. All other parameters that we learned for PN junctions still apply. Okay, saturation current, the current for the collector and the emitter, they are all based on the Shockley equation. So as you can see right here, similar to the diode equation, ID is equal to diode current is equal to saturation current times E raised to VD over VT. The diode voltage, meaning the voltage at both terminals of that junction, right? So it follows the similar structure. Now, this is basically the SPICE description of a BJT, right? SPICE description of a BJT. The model number is 2N3904, and it states it's NPN, okay? NPN. Again, saturation current is part of the spec, similar to the PN junction diode, is a function of the geometry, the design, and the doping profile. Okay. Let's see. We'll look at all other terms later on. But let's go to behavior and then the physical physical construction of a transistor. So normally we'll think a BJT is a three-terminal device. It consists of three separate semiconductor materials. And these semiconductor materials are connected back to back. So we could have let's do it this way. Okay. We have three separate semiconductor materials connected back to back. Now, the type of semiconductors, we have only two, P and N, PN junctions, right? So if you connect a PN junction and a third P-type material, we get what is known as a PNP transistor. And let's just do this. And if we take the P-type material in the middle and sandwich it between two N-type materials, we get what is known as an NPN transistor. Okay, PNP and NPN. The only difference between the two is that in one of the transistors, electrons are the majority carriers. In the other one, the holes are the majority carriers. Guess which one is which? Which transistor has holes as the majority carriers? PNP. Well, because it's twice as many N-type materials, but that's not the reason. So holes are majority carriers. And here electrons are majority carriers. Now, so far we always say majority and minority carriers. Well, the name bipolar junction transistor, junction is just, it's a PN junction transistor. Transistor, one of the earliest explanation for this was it because it transfers resistance or transfer resistor. And the bipolar comes from the fact that the electric current is a function of both electrons and holes, both negative and positive charges inside the same device. So if you have electrons as the majority carrier, you have holes as the minority. And if you have holes as the majority carriers, you have electrons as the minority. So the electrical current is a result of both kinds of charges. Hence the name bipolar junction transistor, which, if you think about it, even the diode is a bipolar device because the electric current is both electrons and holes. Okay, electrons and holes. All right, so it's a sandwich layer. We would think that if it's two back-to-back PN junctions, current would just go in opposite directions, right? If it's an NPN transistor, it's a PNP transistor, depending on which transistor we use, we'd expect that the current's either going in or the current is going out, right? But that's not what happens. And that is due to the physical construction and the doping profile of these semiconductor materials. So it goes a little bit against the techniques or the circuit analysis that we have done so far for the PN junction. Okay. So the emitter control, there are three modes of operation. We look at those modes of operation. There are three regions of operation. We'll again look at those two. But in general, the collector terminal does not conduct a lot of current. Okay. Which is, again, we'll talk about it just in the next few slides. Okay. So it does not, it does not control the flow of current. Okay? It conducts a lot of current, but it does not control the flow of current. Remember what I said, current flows between the collector and emitter, and the base is the terminal that controls the flow, right? So the base is the one that controls, but it does not control, excuse me. The base terminal controls the flow of current, but it does not conduct a large current. It does not conduct much. The emitter can both control as well as conduct. And there's a reason for that. Okay, so emitter can do both. It can control as well as conduct. Collector does not control much, but it can conduct current. Okay, so far so good. Okay, so if we say let's stick with NPN, right? Most of the classes across pretty much, if you take a class anywhere in the world, the description will always begin with an NPN transistor. The NPN transistor is the most popular version, for the simple fact being that electrons have higher mobility than holes. Electrons can move much faster because they are not they have higher mobility because they are not restricted simply by the spot in the lattice structure. They can move anywhere, right? Whereas holes are restricted to certain fixed spots. So electrons have higher mobility than holes, so you can create faster devices with with an NPN transistor versus a PNP transistor. So NPN transistors are very popular. PNP transistors require a little bit of design to match the speed of an equivalent NPN transistor. Okay, so most of our explanation will be with regards to NPN transistor, but the exact same thing applies to a PNP, except the electrons and holes are switched, and the current directions and the polarities are also switched. That's the only difference. Okay, so we say that the collector terminal conducts, right? The collector base junction, so this would be the base. Let's say this is collector and this is emitter. So we have a PN junction between the collector and base, and we have a PN junction between the base and emitter, right? Now, if you look at the polarity right here, what do you see? If it's an NPN transistor, as what we have here on the left, this is NPN. On the right, we have a PNP. The base is higher voltage than the emitter. So it's an NPN transistor, and this base is at a higher level than the emitter. Is the junction forward bias or reverse bias? PN junction, base emitter, PN junction base is at a higher electric potential than the emitter. Forward bias. So it's forward bias junction. It behaves like a regular diode. Okay, regular diode. Whereas when you look at the collector and base junction, and it's not marked here, but the collector base junction is actually reverse bias. Okay, so the CB junction is actually reverse bias. And this mode of operation is known as the forward active mode for a BJT. So if the collector base junction is reverse bias and the emitter base junction is forward bias, this is known as the forward active mode, sometimes simply known as the active mode. There is a reverse active mode, but that's not something we study. Okay. Reverse active is basically the transistor is completely off. Nothing can happen because both junctions are reverse bias. So if we say that the base emitter junction is forward biased and the collector base junction is reverse biased, two questions arise about the device operation. First, if the junction is forward bias, then we would assume that there should be a large current flow through that junction, right? So then that question is, how come the base current is very small? And the second question is, if the collector base junction is reverse bias, how come the collector can conduct so much current? Right? So those are the two questions. And the answer lies in the physical construction of the BJT. So in reverse bias, when you take a PN junction, we say it does not conduct much current, right? The current is typically in nanoamps, picoamps, and even femtoamps, very, very small. And in reverse bias, the reason the current is small, because that current, the reverse saturation current, IS, is a result of the minority charge carriers. crossing the junction, right? You have a PN junction. So you have N-type and P-type. You have an excess of holes, here, and minority carriers are electrons. And here, the minority carrier is a hole, whereas excess of electrons. Reverse biasing means you're applying a positive voltage at this terminal, which attracts the holes, right? So if you have minority charge carriers that are present in the N-type and minority charge carriers that are present in the P-type, if you apply a reverse bias, they are going to be attracted. They are able to cross the junction, and then current starts flowing through the device. But the key word is minority, because minority means it's very low in numbers. Because it's low in numbers, the current value is also very low. Everybody with me so far? Okay. So if you have, instead of having, as in this illustration, we have like one electron and one hole on each side, right? Instead of just one, let's say you have a plethora of minority carriers. So instead of low number of minority carriers, what if the number is higher? Okay. What happens? What do you think would happen? If you have, forget the word minority for a second, because in this case, it applies as in the number is low. What? Just focus on the fact that in a P-type material, you have a large number of electrons available, and they're close to the edge of the depletion region. So if they acquire sufficient energy to cross over the junction, what happens? Current, and large value of current. And the same thing happens for the holes. And that is one of the key operating principles of a BJT. Okay. So in reverse bias, we do have some amount of current flowing. We refer to it as saturation current because it saturates to a very quickly to a level, and that level is typically nanoamps, picoamps, and femtoamps, very, very small, because of the low number, or the small number of minority charge carriers. Okay, so let's look at what happens in forward bias. In forward bias, N-type material is connected to P-type material is connected. So here we have holes, here we have electrons, right? N-type and P-type. And so now they are pushed towards the junction. These majority carriers acquire enough energy to cross over the junction, and they diffuse through, and large amount of current flows through. So if you have a heavily doped P and N-type material, you have a large number of majority and minority carriers that are available, right? So the number of doping increases the amount of current that can pass through the junction. More carriers, more current. So far, so good? Right. Now let's take these two, reverse bias phenomena and the forward bias phenomenon, and put it together. Okay. So the BJT design is very unique. The doping profile is also very unique. If you have an NPN BJT, we have a P-type material sandwiched between two N-type materials. Now, the physical geometry and design is such that the base, which is in the middle, is very, very thin, or very, very small compared to the emitter and the collector. Okay. In fact, in the physical construction, the collector is actually far larger than the emitter and the base. Okay. So the collector basically is, you have the emitter that is embedded inside the base, which is inside the collector. So looking at from the top of the surface, that's how it looks like. So the collector is far larger in surface area compared to the emitter and compared to the base. Okay, so the base region is very, very thin. It's very, very small. Emitter is somewhere in the middle of the base and the collector, not just surface area, volume. And then doping profile, emitter is the most heavily doped semiconductor material in a BJT. And because the emitter is the most heavily doped material, it emits the charge carriers, hence the name emitter. Again, emitter is the most heavily doped material in a BJT, whether it's a PNP or an NPN, doesn't matter. It's the most heavily doped, so it emits the charge carriers, hence the name emitter. Collector collects the charge carriers, hence the name collector. And then base forms a operating base whereby we can actually control this emission and collection. Okay. So base, it's very, very thin. Emitter is smaller in surface area, but not as thin as the base. And collector is the largest. Okay, is the largest. Now, the doping profile. Emitter is the most heavily doped. Collector is very lightly doped. Base is also very lightly doped. Okay, so there aren't as many free charge carriers present in the base and the collector. So these are not regularly, these are not normal doping profiles for a PN junction type device. Okay, again, the emitter is very heavily doped. The base is very lightly doped. And the collector is, well, use the words extra lightly doped here, but I'll explain what it means. So this is relative. Doping profile. The emitter doping is greater than the base doping, which is greater than the collector doping. So in general terms, collector is the lowest, base is somewhere in the middle, and then emitter is the highest. So the very heavily doped and extra lightly doped, that's relative to the base, right? Collector is lightly doped with relative to the base. Emitter is much more heavily doped than the base and the collector. So what's happening is, what's happening is you forward bias a base emitter junction. Oh, is everybody clear on the construction? Okay. Any questions about the construction of the device and the doping profile? Okay, so emitter is very heavily doped. NPN transistor, you forward bias the base emitter junction. So the emitter starts emitting electrons. A large number of electrons are going to cross over the base emitter junction. Okay, large number of electrons. So there's a party going on here. There's a large crowd of people who has gathered. They have arrived to the party, but there's nothing much to do because the base is very thin and there are not many people around. Now you reverse bias the collector base junction. If you reverse bias the collector base junction, meaning let's say this is N, this is P, and this is N. So here you're applying a positive voltage with reference to the base. Okay, with reference to the base. That's basically the depletion region. So it should come right here. So now you have a large number of electrons that are in the base with nothing to do. Some of those electrons will combine or recombine with the holes that are present in the base. but the base is very thin and lightly doped. So the large number of electrons that arrive, only a small portion of those electrons will recombine with the base, and that will constitute the base current, very small. The rest of the electrons, they're hanging around, don't know what to do. And that's where the reverse bias comes in handy. If you now apply reverse bias to that N and P junction, well, electrons are a minority carrier in the base. Because base is p-type, electrons are minority carriers. And we just saw a couple of slides ago, what happens to minority carriers in a reverse bias junction? They are pulled through the junction and they are swept away through the collector. And that's why the collector has a large current flow, even though the collector-based junction is reverse bias. Let's take a pause while you think over that. Let me know if something doesn't make sense and you have questions. Did all of that make sense? Which one? Forward bias. Any questions? Did everyone understand why it doesn't function like just two back-to-back PN junctions? No? Yes? No? Okay. Where are the questions? In general. Okay, let's recap again. We have an NPN transistor. Let's draw some visual aids. Very thin. Just a few number of holes. Whereas here, large number of electrons. Okay. This is forward bias, and this is reverse bias. So that is what is shown by this junction right here. This is the depletion region for the forward bias, so it shrinks. This is the depletion region because it's a reverse bias, so it expands a bit. Okay. And of course, the geometry and the design of the BJT restricts how much it can expand. So these electrons, when you forward bias them, are going to cross over into the base. They're moving from the right to the left. So they're entering the base. Now, when they enter the base, if it's a normal PN junction diode, just going to go through, right? And current starts flowing. So if the base was wider or bigger and would be normally, would the normal doping very close to the emitter doping, then it would behave like a p-n junction diode and everything would just flow out through the base. Then the BJT would not work. Okay. So the key point here is the emitter has a large number of electrons that outnumber the number of holes in the base. If the base was the same size as the emitter with about an approximately equal number of holes as the electrons in the emitter, they would just recombine. You'd have large current flowing out of the base. That would be a normal p-n junction. But because the base is very thin, electrons come over, a very small portion of those electrons from the emitter will recombine with the base, with the holes present in the base, and the rest of the electrons are free to cross over because electrons are minority carriers in a p-type material. So if we reverse bias the collector base junction, those electrons acquire sufficient energy to cross over the base and come into the collector. So electrons come over here. Some of them recombine and flow out. That becomes the base current or constitutes the base current IB. But the majority of them are able to cross over here because electrons are minority carriers in a p-type material. The number of holes in the collector is also far less. But because it's reverse bias, because the collector base junction is reverse bias, electrons are now free to actually move through. Yes.
Okay, I can imagine the current on, but then once it's on, like how is it able to turn back off again once you adjust the voltage of the base?
So that's a good question. So question is, we understand how we can turn the transistor on forward active mode, but then how can we control? So that's a very good question. The control comes from applying an AC signal at the base. So remember I said we apply a DC voltage, we set up a bias, we prepare our device to accept AC input signal. So we apply an AC input signal at the base, which is alternating. And when it alternates, it's going to change our Q point. So it's going to vary the current or the number of electrons that can cross over. So depending on the AC signal that's applied at the base, a large number of electrons, well, not large, but larger than normal can flow out, or lower than normal will flow out. So it'll either add to the number of electrons or subtract from the number of electrons. And it would seem like it's a small, small proportion, but that's how the amplifying action works. Okay. So in the transistor terminals, we have, sorry, in the PN junction diode, we have an anode and cathode. If we want to control, we have to either vary the voltage or the current that is being applied at those terminals, right? In a transistor, the base is the one that controls. And this control happens due to the AC input at the base. And of course, this, what we are covering today, the physics of operation, is an entire field of study by itself. Like there's an entire course that students take, and we are just covering it in one single lecture. Okay. So that's, of course, not the primary purpose. Our purpose, of course, is to study this device and see how we can apply it. But we are, according to syllabus in the material, we are required to cover some of the fundamentals and basics. So transistor terminal specialization, again, collector can conduct and carry the flow, base can control the flow, and emitter can control and carry. Okay. The emitter can function both as an input and output terminal. The emitter, the base is input only, and the collector is output only. Okay. So each of these terminals will have a specific purpose just because of the way the device is constructed. Okay. If the base is common, sorry, not the base. If the collector is common between the input side and the output side, we call it the collector common collector configuration. If the emitter is common to both the input and output side, then it's known as the common emitter configuration. And if the base is common to both the input and output, then it's the common base. By that, I mean, if you have a system with 3 terminals, you have one terminal that is common. This is the input. That's the output. So one of the terminals has to be common to both the input and the output side. So depending on which terminal that is, we call it common collector, common emitter, common base. By far, the most common configuration is the common emitter, CE mode. Okay, common emitter mode. So what we are going to do is we're going to look at amplifier characteristics, because what we want to do is we want to use the BJT as an amplifier. There are 3 modes of operation for a BJT, or 3 regions of operation. Okay, there is something known as active mode, then there is cutoff, and then there is saturation. Okay, and we'll look at these again later on in this chapter. There are 3 modes of operation. When we use it in active mode, we can use the BJT as an amplifier, and that's what we are looking at. We are not looking at anything else. In cutoff and saturation, it can work as a switch, as an electronic switch. Okay, and that's why I was a little bit confused at the beginning when a question about the switch was asked. So the transistor can work as a digital switch. Okay, if it's in cutoff, it means the switch is off. If it's in saturation, it means the switch is on. But we look at those regions of operation later on. Okay, right now let's cover the amplifier. So if you have an amplifier, depending on the configuration of the BJT, we can use it as a voltage amplifier or a current amplifier or as a power amplifier. If we use it as a voltage amplifier, then the voltage is amplified. The current between the input and output may remain the same or may even be less than the input. In a current amplifier, any current that is applied at the input will be amplified at the output. The voltage at the terminals may remain the same, or it might even be lower at the output. In a power amplifier, both voltage and current are amplified. Okay. Amplification simply means output is larger than input or greater than input. Okay. Output is greater than input. Gain of an amplifier or gain of a system is always output quantity over the input quantity. If the gain is greater than 1, then we refer to that system as an amplifier. If the gain is less than 1, we refer to it as attenuator. Last week we did attenuator. Next week we're going to work with amplifiers. Okay. So we can use many different configurations, but not all configurations are going to work. One of these configurations is shown here. We simulated this. It's an NPN based transistor in the common collector mode of operation. We can simulate it in SPICE or LT SPICE, and we can get an amplified output. Okay. So Computer simulation would work, but it would not work in practical life because of the biasing conditions, meaning the AC source that is applied on top of the DC input may block the DC. On the output side, the DC could get blocked. And so it's not a very good configuration. Okay. This is not something that you're going to build, but as a CPE engineer, if you come across something like this and your system's not working, you're trying to design something, you should at least be aware of what it is, right? So again, the reason that would not work, this is very blurred, is going in like this, and the output's taken, leave here. And then again, there's another one that is the common base amplifier. Again, computer simulation, it works, but in real life, it's impractical. And what we'll actually work with is a NPN CE amplifier. Now, CE amplifier would work. Actually, all amplifiers work, but they would require a lot of design considerations. And those design implementations are not trivial. A CE amplifier, it's like this. Inputs going in, that's the AC and the DC. And the output is taken here. Okay. Emitter is common to the input side and the output side. It's a CE amplifier, but the biasing that is applied would not allow this to work in real life. So the same thing, if you apply an AC source in there, it might block the DC bias. And if it blocks the DC biasing, then the amplifier is not, the device itself is not going to work. So in next week's lab, we're going to work with a couple of different configurations. One of them is going to be a CE amplifier, which is this one. Okay. CC amplifier, the difference between the two, you can see the output for the CC amplifier is taken at the emitter. So the output is at the emitter terminal. Here, the output is at the collector terminal. Okay, and it makes a big difference. And then the collector becomes the common terminal at the input and output in a CC configuration. Common base, again, not very practical just by the design itself. It does find a few applications. And the base simply means it's common to both the input and the output side. Okay. And I believe biasing for linear amplification, that's fine. We are almost out of time. So what I want to just talk about in general is just a little bit about DC and AC. Okay. So DC, when we apply DC voltage, we saw in the diode, we said we set the operating point for that device, meaning we fix the operating point of the device at a particular spot. We fix the voltage, we fix the current. So if you have a BJT circuit, let's say BJT amplifier, and you apply DC bias to it, you apply DC voltage to it, we say we are applying DC bias and we are setting the Q point of operation. Okay. So you apply a DC voltage at the base, at the collector, the emitter. And when you apply the DC voltage to this transistor, it is setting the operating point for that transistor. And depending on the application, whether we want to use it as a switch or whether we want to use it as a amplifier, we set the operating point accordingly. If you want to use it as an amplifier, we set the operating point in the middle of the active region, which is again something that we'll look at later on. And then when it's set in the middle of the active region, now it's ready to accept an AC input signal. So AC input signal is applied. And let's just, for convenience sake, let's just say it's to the base what the transistor is going to do is it's going to take the small AC signal and it's going to take the DC voltage that is being applied as biasing, and it's going to give the shape of the AC signal to that DC energy that is being received. And that's how we get amplification. So the simplest way to state this is you apply a DC voltage, 5 volts, 10 volts, 15 volts, 20 volts, however much you want, depending on your application. You set up the operating point of a transistor, then you apply an AC input signal on top of the DC. It will take the DC and give it the shape of the AC input signal. Okay, that's the simplest explanation for a BJT amplifier. That's where the energy comes from. Okay. All right, so we'll end class here today. I'll see you all on Monday. I did post an announcement about the Friday quiz, so please read it if you haven't already done so. Monday, we'll have a Monday quiz as usual. I'll post an announcement, be based on the material we have covered in the diode section. One other thing I wanted to point out was this. If you have not looked at the national labs, Lawrence Berkeley National Lab is one example. Very close to here in California. They have a lot of summer internships available for undergraduate students. There are summer internships for computer science, data science. There is, let's see, yeah, computing sciences summer program. So if this is something that might interest you, definitely go ahead and apply. Okay. I have no idea. I don't know. So if you just search for Lawrence Berkeley Lab, LBL, that's one of the national labs. There's Lawrence Livermore also. There's Sandia. There's like national labs all across the US, but this one is one of the closest ones, and they have several internship opportunities. All right, have a good weekend, and I will see you all on Monday.